This is Dr. John Stewart. I'm the president of Biophysica. And in the last year, I developed a few new designs that I want to share with you today. The first one is a double meter that I now try to put in all of my devices. The upper scale here is voltage. The voltage is right across the electrodes in the water. And the lower one is the current in milliamperes. It's going right through the water. So they're very direct, accurate indicators of voltage and current. And when you have voltage divided by current equals resistance, that's called Ohm's law. So we are working under the rule of Ohm's law with our water, because the water that we're using is mostly distilled water, which when you measure with your conductivity meter, for example, typically this conductivity meter will indicate your initial beginning conductivity of the water, which might only be about 1 or 2 units of conductivity, called microsiemens. So, but that's how we start, because the colloidal, the distilled water is pure, readily available, and inexpensive, and in some ways more convenient than reverse osmosis water. So there's the calibration, the conductivity meter that I recommend. You can buy this on Amazon, or you can buy it from me at a higher price, of course, because I have to order it from Amazon, but it's quite useful, and it will indicate how the water, your water is becoming more and more conductive. So let me show you now. This is a single channel, single channel colloidal generator, and we have a current control knob and a voltage control knob. So we can turn the voltage down to a very low level or to a very high level. There's inherently 100 volts available. And this overcomes the problem of distilled water, which can take hours or days to break through that resistance. So what I'm going to do now is I'm going to attach a dummy load of about 1,000 ohms, and that you'll see now that I'm getting a reading on the current meter. That's the current meter. So I can get a reading, and you can program for this size of electrode, 2 inches by 6 inches. We don't want to go more than 1 milliamp per square inch. So 2 by 6 is 12. Don't go above 12 milliamps. And you can adjust, bring the voltage down to a minimal level. I've found that when the voltage is so high, it can do damage to the nanoparticles. So we want to get the voltage down as low as possible, but yet consistent with the desired milliamps, around say 10 milliamps is what I use. This is a single channel. This is the dummy load, and this new double meter arrangement will be in all of our instruments, including the 2-channel domestic model, the CS2-45. Also remember that in here we have alternating polarity. That was the alternating polarity switch. So if you're doing colloidal gold, then turn the alternating polarity off. A new problem that we're dealing with now is zinc and copper. Zinc and copper electrodes acquire a very thick deposit of oxide that prevents further release of the atoms. So let me show you what here is a typical brand new copper electrode. You see the nice copper color of the metal, the pure 99.99% pure copper. And this plugs in, two of these plug into my machine. But unfortunately, when you do that, you get this coating over the copper and the zinc that prevents release. So what my new plan is to have, instead of alternating back and forward, where one is the anode, then the other one's the anode, it's when these metals are cathode that they acquire this deposit. So what I want to do now is have one copper or one zinc and as the anode, which is releasing the positive, and a stainless steel receiving electrode, the cathode, so that the active electrode, the copper, is releasing all the time and never gets a deposit on it, because we don't want this oxide layer deposit to form. But the stainless steel is impervious and is easy to clean. So that explains the nature of this new voltage current double meter. So we'll stop now, and I'll see you again at the next video. Thank you.